This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Okay, so today is to try to put the physics and the astronomy and the science goals onto the picture that I talked about last night in my public lecture, and I think most of you were at the public lecture, and now we're going to try to really understand much more about what's going on with gravitational wave detection and why we're doing it. Now, there are two lectures. The first one I'm calling Sources of Gravitational Waves. I think I gave a slightly different title about compact objects and their gravitational waves, but it's the same subject, a little bit broader than just the compact objects. But I want to talk about gravitational waves generated in astronomy, the waves that we want to detect, from the point of view of understanding how strong those waves can be, what are the goals, what are the sensitivity goals for detectors, why do we have to build detectors that are as sensitive as the ones that we're building, and also then what kinds of information would we get from observing gravitational waves. So I won't say in this first lecture very much about the detectors themselves. I'll ask you to just accept that we will have detectors that do certain kinds of things. But then in the second lecture, I'll go into the techniques of detection, the principles underlying detection, and some of the physics challenges of building gravitational wave detectors. So that's the introduction. I'll start with this quote from a book by Harry Collins. And what he says is gravitational wave detection is about seeing the biggest things that ever happen, collisions, explosions, and quakings of stars and black holes, by measuring the smallest changes that ever been measured. And I think that puts it in a nutshell, that contrast of looking for something that's really important because they're big, and having to look for it with something extremely difficult to build, a very sensitive apparatus, because the changes that you're measuring are very small. Now, Harry Collins is a sociologist. He's not a physicist. He gained notoriety, actually, in the physics community at one time by getting into a debate in the pages of Physics Today with some physicists about, is the world real? Are what we doing as physicists real? Are we describing the real world, or is it just something in our... So for a while he was a person who was kind of anathema in the physics community. But then he got interested in gravitational wave from the sociology point of view. We have a big collaboration. We've been building it up from a small beginnings of about 20 or 30 people, and now we have something like 1,000 people working worldwide on this, and he wanted to understand as a sociologist how it works. And so he came to us, and we concluded an agreement that he has access to the collaboration and to all the internal documents, and he can come to all our meetings and listen to everything we say, and then he can write his books about how we work. And he's not supposed to divulge things that we think are confidential, but he does talk honestly about how big collaborations work in physics. It's very interesting. This is his first book. He's got 3 or 4 books and some articles. So in a sense, we're his lab rats. He comes and we're just doing what we think is important, and he's watching what he thinks is important. But he's been converted to physics. He now thinks that physics is real. This is really interesting. The last big collaboration meeting, he was invited to say something, and he got up and he said, those gravitational waves are out there, and you guys are going to see them. And he's such a fan of this big collaboration. And I think one of the things that it brought home to me about organizations, and this is a serious point set aside from the rest of my talk, but a physics collaboration, and gravitational waves is one. We have a thing called the LIGO scientific collaboration, which is a voluntary organization of 600 or 700 scientists, and then there's other collaborations that we have agreements with. These are self-governing in a way that is very different from our political institutions. The way we govern our countries and our cities and so on is kind of hierarchical, and there's a lot of competition to get up at the top, and then there's a lot of reward and so on. And there's a lot of discipline and so on. In the gravitational wave collaboration, like in other big physics collaborations, like particle physics is another example, we kind of model ourselves on particle physics collaborations. They're very, very, they're entirely voluntary and consensual. And so we have a spokesperson who's elected periodically and who has almost no power, who has does lots of work to keep everything going. People come and participate, and we make decisions kind of democratically, based, of course, on the physics, not just on prejudice or political orientation or something like that. We have very clear guiding principles, but we make these decisions collectively, and then they're implemented by a bunch of people who do a lot of work without any extra reward, and carrying very little power. It's a very, very different kind of social structure, and it's kind of amazing that it holds together the way it does. But I think for Harry, that kind of thing is very interesting, because he wanted to figure out, how do we make decisions? Who are the really important people? Because it turns out that there is a hierarchy of scientific respect and so on, and if the top people say they think this is what should happen, then generally the collaboration will do that. But it's done in a consensual way rather than in a way that is enforced in that hierarchy. But anyway, so the sociology of these big collaborations is something that's of interest to people outside the collaborations. And Harry is a kind of translator who's written several books now on the history of gravitational waves. Now, let's go into gravitational waves, and I want to go through and highlight the most important points about the physics of gravitational waves. You've had detailed lectures about gravitational waves and perturbation theory in general relativity. I want to just highlight the things that are the most important things for the observational point of view. The first point to make is that general relativity might not be correct, and therefore, well, as I said last night, it's certainly not a quantum theory, so that there are going to be corrections to it at some level. And it could be that those corrections affect gravitational waves in terms of the speed or the polarization. So those are things you want to be alert to when you're making gravitational wave observations. The information that it carries is probably obtainable in no other way, so we want to be able to read it. The equivalence principle is a fundamental principle and is incorporated in many alternative theories of gravity as well, to general relativity. And because the equivalence principle, it means that gravitational waves operate by tidal forces. So if you're in free fall, there's no gravity. That's what the equivalence principle says. So if a gravitational wave comes by and you're sitting here in free fall, you don't feel it, no matter how strong the gravitational wave is, except if you're big enough that the differential action of the gravitational wave across your body or across your apparatus is measurable. And that's the tidal part of the gravitational wave. So the overall sort of local acceleration, not something that you can feel. So if you want to build a gravitational wave detector, it has to be that you're looking for the differential part of the acceleration. You're looking for differences in acceleration at different places. That means that detectors have to be, that they gain an advantage by being bigger, because you're looking for something which, to first order anyway, increases linearly with length. In general relativity, the speed of gravitational waves is the speed of light. The metric can be described as a perturbation on some background, and that perturbation conventionally is called h, and it's also usually a very small perturbation on whatever is the effective Newtonian gravitational potential. In general relativity, only two transverse polarization modes, and the stretching is conventionally, what we call H turns out to be twice the tidal distortion delta L over L. The tidal distortion is the gradient of the acceleration, as I've just been explaining, which means that in Newtonian terms it's the second gradient, second derivative of the Newtonian potential, and that is represented in general relativity by the curvature tensor. And so what we're really measuring with gravitational waves directly is the curvature tensor. The most sensitive detectors we can build at the moment are interferometers, and they're linearly polarized detectors. And all the detectors we build are polarized detectors. So we talked a bit last night in the question session about polarization. It's important to have detectors with different orientations, so you're actually picking up different polarization modes. Now, very simple. I think these equations must be familiar to you. There's a gauge choice, which we call the transverse traceless gauge for linear perturbations of a Minkowski background. And if you go into that gauge, then the equations without a source, the propagation equations for the gravitational waves, are very, very simple. It's just the wave equation. It looks just like the equations for electromagnetic waves. You've probably seen some picture like this. This is the polarization diagram. This is the action of gravitational waves. If you imagine that you have a ring of particles that are out in outer space, they're free to move. There's no connections between them, and then a gravitational wave comes in from the direction onto the plane of this picture. Then one of the polarization states would be to distort that circle into an ellipse, and then because it's a wave and it's oscillating, you get an ellipse with the same axes, but with the major and minor axes reversed, and then it goes back to being a circle. So the full one cycle of the wave takes you that way. The orthogonal polarization, because it's tidal, is actually just a 45-degree rotation, and so your axes go that way, and then it's on that side. With these two polarizations, you can describe any gravitational wave with a linear combination of those two polarizations. And so now if you our detector of choice, and I'm going to be talking about detectors in the second lecture, but our detector of choice today is the interferometer. And this is a simple sketch of an interferometer where you have light coming in from this side through a beam splitter out along two different arms. And if you imagine placing the mirrors of those two at the endpoints of those two arms on this circle, this is the ellipse, this is the polarization circle that I had drawn before. If you just put those as two particles on that circle, and if you put the beam splitter right in the middle of the circle, then when the gravitational wave with the top line of polarization distorts that circle into an ellipse, what it does is it moves this mirror further away, brings this mirror in closer, and that automatically then creates a change in the interference pattern at the beam splitter. And the beam splitter, the way that works is if you've normalized, if you've arranged in such a way that when there's no gravitational wave, there's no light coming out here, you have complete destructive interference. Then when there's a gravitational wave, you'll have light coming out here, and that'll be your signal. And so you're just reading off the intensity of the interference coming out, and that's proportional to the gravitational wave signal. So that's a simple way of describing it, and it shows that interferometers are essentially ideal for detecting gravitational waves. It's exactly the kind of thing that you want to be doing. And the history of interferometers as gravitational wave detectors goes back quite a long way. The other thing I want to mention, and I used this term last night, standard Sirens. For certain kinds of gravitational wave sources, including the most common that we expect, which are binary systems in orbit around each other, if the binary is shrinking, as the Hulse-Taylor binary pulsar is, and as almost all the binaries are that we're going to be detecting, certainly in the near future, if there's a rate of change that you can measure of the orbit, then that, of course, translates into a rate of change of the frequency of the emitted gravitational waves. If you have that information in the signal, then there's a combination of the things you can measure that gives you the distance to the source. So it's just a number out in front, which I won't talk about very much, 1 over the frequency squared of the gravitational waves, the chirp time, which is the time scale associated with the rate of change of the frequency, so if you can measure that, and the amplitude h, which you're measuring. This combination has the, remember h is a dimensionless number, so this combination has the dimensions of distance, and if you're on a cosmological scale, it's the luminosity distance out to the gravitational wave source. There are factors, there are numerical factors out here which have to do with orientation. So the gravitational waves that you're measuring, you have to make sure you can measure their polarization. You have to understand the orientation of the source and everything, the number of angular things that you have to work out before you can get the distance down. And so I've left those out because they tend to be a little bit complicated to look at. But this is an extremely unusual situation in astronomy, that you can make a measurement and know how far away your source was from intrinsic information in the signal. And that's a calibration then of distance ladders. We hope to tie that to the distance ladders that are used in astronomy. As I said, every neutron star binary system, every black hole binary system that will be detected by LIGO will be coalescing. And so we'll have all of these numbers, and we will be making distance estimates for each source. Now, I want to talk about the generation of gravitational waves, and again, I'm building on things that I'm sure that you've seen. Excuse me, the coupling of gravitational waves to the distance changes is given by that proportionality. I left out the factor of 1/2. I should have put that in there. Everything on here is actually, I'm not worrying about factors of 2. I'm trying to get you to order of magnitude estimates for the strengths of gravitational waves. And h is the amplitude. Now, there's a thing called the quadrupole formula, and I guess you've had the quadrupole formula, which is the fundamental formula for the generation of amplitude of gravitational waves in the slow motion limit, just as for electromagnetism, the dipole formula is for charged particles. It turns out that if you look at the quadrupole formula and manipulate it a little bit, and just try to get scalings out of it, try to get order of magnitude estimates, it turns out to be very, very simple. The quadrupole formula has things in it like the density, the mass density. There's an integral over the volume of the system. If I just replace the integral over the volume of the density, if I replace that with the mass of the system, then I get some scaling, some order of magnitude estimate. Inside the integral, there are coordinates. There's x's with different indices on them. If I just replace each one with the size r of the system, excuse me, and I'm using capital R as the dimension of the radiating system, then I can simplify my formula. And there's time derivatives in the quadrupole formula, and I can replace, for a self-gravitating system, I can replace time derivatives, which are basically velocities. I can replace those with the gravitational potential, because I have the virial theorem for a self-gravitating system. When I do all of those things, and it's all just order of magnitude stuff, I get a very simple formula, which is that there's an upper limit on h, which is the product of just 2 Newtonian potentials made dimensionless by scaling with 1 over c squared. One is the internal potential, the mass of the system over its own radius, and the other is the Newtonian potential of the system at where we are, because little r is the distance from the system to us. So this is a very tiny number, the gravitational potential of the system, which is very far away at our location, and this is the internal number. And it's just the product of those two Newtonian potentials, is an upper limit on h. It's an upper limit because of considerations of symmetry. You I'm sure, also realize that if I had a body that's perfectly spherical and it's pulsating in a spherical way or collapsing in a spherical way, it doesn't give off any gravitational waves at all. So I would still get the same scaling for that body, but I'd have zero, h would be 0. So this is an upper limit which can go all the way down to 0 if I have perfect symmetry. But it's also an upper limit that's attainable. So if I take a maximally asymmetric system, which is two equal mass stars in an orbit around each other, that's a perfect quadrupole system. It turns out that formula works very well. That's an attainable bound for the amplitude of gravitational waves from a self-gravitating system. So it works only for self-gravity because I use the Virial theorem. It's not working for springs with masses on them. But that's a very useful formula because you can immediately plug some numbers into it and ask yourself, what are the numbers that are appropriate for targets for building gravitational wave detectors? How sensitive do I have to be? We'll do that in a minute. But also I want to point out that that gravitational waves fit in with classical physics, and if for other wave fields, I always talk about the energy that's carried by waves and so on. And if you look for electromagnetism and you write down the energy formula, excuse me, in terms of the vector potential, or if you look for a scalar wave and you look at the energy flux formula in terms of the amplitude of the scalar wave, you find that there's always, it's always proportional to the square of the time derivative of the amplitude of that field. And that's also true in general relativity. The energy flux is proportional to the square of the time derivative of h. And then, of course, if I know I need that, then all I have to do is put in look at what are the fundamental constants I need to get the dimensions right for energy flux. Energy flux is energy per unit time per unit area. So if I put in c cubed over g, you can trust me, that comes out to be something with those dimensions. And then I'm almost done, but then I need to know what the factor is in front of it, and that's where all the work is. That I have to spend 3 days calculating on a piece of paper to get the 1 over 32 pi. But if I didn't care about the 1 over 32 pi, all the rest of it is something I can just write down without even thinking if I believe that general relativity fits in with all the other classical field theories, okay? So I'm not trying to trivialize the 1 over 32 pi. I'm trying to point out to you that we fit here. This is a formula you would see in any classical field theory with appropriate dimensional constants and then some factor out in front. So that's the energy flux carried by a gravitational wave. And from that we can calculate luminosities, and I'm about to do that too, and come back to this question of how incredibly luminous gravitational wave sources can be in terms of energy. So let's do some simple estimates. Let's talk about the amplitude formula. Here, if I take a mass of 1.5 solar masses, that's a typical mass for a neutron star, 1.4 or something like that. I'm not going to worry about small differences between numbers, but I'll take a number about 1.5 solar masses. If I say, I've reversed these, sorry. If I say the size of the object is 10 kilometers, that should be big R is 10 kilometers. That's a typical radius for a neutron star. And if I place the object far away at 100 megaparsecs, I mentioned that number last night as a distance we think that our nearest neutron star binary coalescing during a one-year observation might be, 100 megaparsecs. That comes from our understanding of astronomy, that distance scale. If I put all those numbers together, I get h around 10 to the minus 21. Immediately tells me, that's just this formula here, that immediately tells me where I have to go with my detector sensitivity. No good having a detector that detects h at 10 to the minus 12, which would still be a wonderful thing to build, this tidal effects of 10 to the minus 12 but it's not going to detect interesting gravitational waves. I could do this amplitude thing for many different kinds of sources. I could work it out for other things, but typically I always wind up saying that I need to be around that. Supernova used to be very important to the discussion of, and motivation of gravitational wave detection, and the nearest supernova, a supernova also might involve forming a neutron star about that radius, but the nearest supernova is going to be closer than this. The nearest supernova could be a factor of 1,000 closer than this. It could be 100 kiloparsecs, which is roughly the distance to the Large Magellanic Cloud. And the most recent supernova nearby was in the Large Magellanic Cloud, which is 50 kiloparsecs away. So if I take that a factor of 1,000 away from that, then I would boost this number to 10 to the minus 18. And 10 to the minus 18 was talked about for a long time as a goal for gravitational wave detectors. But what it leaves out is this upper bound. It is an upper bound, but there's this geometrical factor here which can go right down to 0. And what we understand about supernova explosions now from detailed numerical simulations of the process is that they're nearly spherical, is that they're not highly asymmetrical. And so they're not coming anywhere close to that 10 to the minus 18. And so again, we're being pushed down to 10 to the minus 21 or smaller for a nearby supernovae. And that's the picture across the whole spectrum of different gravitational wave sources. Okay, the flux, the energy flux, leaving a black hole merger. Let's take the strongest, intrinsically strongest gravitational wave thing we can imagine. You have two black holes, they're in orbit around each other, they're about to merge. Because they're in orbit around each other, their velocities are typically the velocities close to the speed of light. The gravitational wave distortion is immense. The perturbation in the metric is of order 1 nearby. So I'm looking at the energy flux just outside the system. So I'm going to take h to be of order 1. The time derivative will be set by the fact that the velocities are of order the speed of light. So that means the time derivative is c over the size of the system. The size is determined by the mass to factors of 2, and so I'm not going to worry about. That's the time derivative. If I put those things in a hand-waving way again, I get a number which is c to the 5th over 32 pi g m squared. This c to the 5th over g, this is c cubed over g, but when you talk about the flux, then you're adding in this c, so you wind up c to the 5th over g. Is an important number, and I'll come back to that. And it scales as 1 over m squared. That's the energy flux. That's energy per unit time per unit area on a little sphere just surrounding the black hole system. So that's interesting, but we're not near there. But why don't we just integrate that over the sphere and get the total luminosity? If I do that, I'm just going to integrate by taking that flux number and multiplying by the area of a sphere of radius m, 4 pi m squared. And then I get the total energy leaving that sphere. I get the luminosity. And that gets rid of the m squared, and I get c to the 5th over g with a factor of 1/8 in front of it as well. C to the 5th over g, interestingly, is a pure number, is a pure combination of fundamental constants. It has the dimensions of luminosity. It is energy per unit time. And it's a huge number because g is tiny and c to the 5th is large. And so it turns out to be 10 to the 52 watts. This number with the 1 over 8, 10 to the 52 watts. Where does that fit on the scale of things, 100-watt light bulbs or something? Where does that fit in astronomy? Well, the luminosity of the sun is 4 times 10 to the 26 watts. So this is 10 to the 26 suns. How many stars are there in the known universe? Let's do a little calculation. Our galaxy contains 10 to the 11 stars. Within range of our telescopes, what we can see in an observable universe, turns out there's about 10 to the 11 galaxies. So there's about 10 to the 22 suns in the entire observable universe, and this thing is 10 to the 26 times the luminosity of any one of those stars, okay? So already this thing this number is brighter than all the light being emitted. I mean, this is in gravitational waves. This luminosity of the sun is in light. But nevertheless, when you compare them just in energy terms, the energy coming out of this thing is far higher than energy coming out of all the stars in the entire universe at that particular time of the merger. And that's a pretty astounding thing. I don't know, have I got another line here? Another thing you might know, another thing you might compare it with is a quasar. The most luminous objects, individual objects in the universe are quasars. There are not many of them, but they're as luminous as individual galaxies. So they are actually around 10 to the 37, 10 to the 38 watts. And all astronomers are very excited by how do you get that much luminosity and so on. But 10 to the 37 or 10 to the 38 watts compared to 10 to the 52 watts is piddling. It's very small. So again, a gravitational wave merger at the end of the merger is giving off an energy, more energy than anything else, than the entire rest of the universe together. It only lasts for a tiny length of time. It's only during the merger, which is basically the light crossing time over the system. So it's not, so the luminosity is very high. The total energy that's given off is a more reasonable amount. But anyway, those are the numbers that lead to these astounding estimates. Okay, so this is what we have now in terms of detectors that are operating or are being upgraded. There are two detectors in the United States that are called the LIGO detectors. They're 4-kilometer interferometers, one in the state of Washington, one in Louisiana. There's the Virgo detector, which is a 3-kilometer interferometer in, just outside Pisa in Italy. And there's the GEO detector, which is a smaller one, 600-meter detector in Germany. The arrow somehow got shifted. It should be pointing to Hanover in Germany and not down in Switzerland somewhere. So these three, LIGO, the two LIGO and the GEO, form the LSC, the LIGO Scientific Collaboration that I mentioned. And we have an agreement with Virgo, which is outside the LSC, but a data sharing and joint data analysis agreement. Those are the detectors that are operating. Now, why are there so many detectors, and why are we cooperating? In physics, cooperation is not the rule. At CERN, if you want to detect the Higgs boson, you have two different detector groups, and they don't cooperate. They're rivals. They try to get after the Higgs boson, and of course they publish their independent papers. And we as a scientific community only believe it if both of them get consistent results on the Higgs boson, but they're in competition with each other. Here, we're not in competition. We're jointly analyzing our data. We're pooling our data. And it turns out that LIGO is upgrading now, and LIGO will come online about a year before Virgo. And if we get a gravitational wave detection in that first year, the Virgo people will still be on the paper, even though their detector isn't even operating. That's the form of cooperation that we have. One of the reasons is confidence. We have to be seeing not just random gravitational wave signals, like the two groups at CERN will be seeing their own Higgs bosons. They're not looking at the same Higgs boson. They're just making Higgs bosons and seeing lots of them. But here we're looking at the same gravitational wave sources that are arriving here and then there and then there. And so we want to pool all that data. We can't just say, oh, they saw one and we saw one. We have to make sure we saw the same one and that we extract information from it. One of that forms of information is the polarization, as I described yesterday, and sky location. Another thing is duty cycle. These detectors, when we ran them for 3 years, a few years ago, had a duty cycle of about 80%. That means about 20% of the time they were not in data-taking mode for reasons that they're very, very hard to operate. It's hard to keep them stable. And so it's very important to have redundancy. Another thing is that if you get all the information, you can actually try to reduce the amount of noise, average over the noise of the detectors, and try to extract a waveform. And also discrimination against glitches. This is a very important thing. Glitch is a scientific term, if you didn't know that. It's a term that means something has gone wrong that you don't understand. Lots of things goes wrong in these detectors that are just suddenly something appears in the data, some pop. And it can look remarkably like a gravitational wave signal. But it's only in one of those detectors, and it's not happening in the others, and it's very big, and you know that therefore it's come from the detector. But if you only had one detector, how would you know it was from the detector instead of from astronomy? So you have to compare the detectors in what we call coincidence mode to make sure that you're not being fooled by glitches. We're in an upgrade to advanced LIGO. ADL is advanced LIGO right now. There's an advanced Virgo as well, but this is the slide for advanced LIGO. This is a sensitivity diagram. I will talk more about diagrams like this in my second lecture, but you see numbers here of strain, 10 to the minus 23, 10 to the minus 22. These are measures of H. Here are the frequency band from 10 hertz to 100 hertz to 1,000 hertz. This is the main frequency observing band for LIGO. And so these are basically plots of the noise. The lower down these curves get, the more sensitive the detector, because the lower the noise. And what we expect, maybe 2015, this slide is a couple of years old, but we're on schedule. So we're hoping to turn on the first detectors perhaps by the end of this year. We might have a sensitivity that's a bit like this. It'll be factors of maybe 3 or 4 better than we operated with before, and it might be enough to make a first detection. We don't know. We'd be able to see binary neutron stars, 2 neutron stars spiraling together, 60 megaparsecs away. The Virgo cluster galaxies, to just normalize things, is 20 megaparsecs away and contains a couple of thousand galaxies. Out to 60 megaparsecs, you're a factor of 3 further out, and therefore a factor of about 30 more in volume. So instead of a couple of thousand galaxies, you have maybe 60,000, maybe 100,000 galaxies. We think that there's 1 binary neutron star spiral per year, per galaxy, 1 binary neutron star in spiral per galaxy every 10 to the 5 years. We think it happens in our galaxy every 10 to the 5 years in a typical galaxy. So if you get out to 100,000 galaxies, you have a chance that you're going to see one a year. And so there is a chance that at 60 megaparsecs we might be able to detect one. But that's just an intermediate step, and that blue curve then becomes, this is extended by this brown curve, excuse me, maybe in a couple of years. The laser light is the same, but we're improving the low frequency performance, and we've increased our binary neutron star range to 140 megaparsecs. And at that point, those of us who study the astrophysics are convinced that we have enough range to be detecting a few of these events per year. So sometime between the end of this year and 2017, we should be expecting the first detections. Then later on, we can modify the shape and we can do lots of tricks. But that's the upgrade path that we're on right now. We're also doing a lot of work on the detection algorithms, the data analysis. And I do want to emphasize this, even though I'm not going to put too much time into it. Gravitational wave detection, the data analysis is a crucial component. Of course, any experiment, you have to analyze your data. But all the signals that we're seeing, all the signals we expect to receive, these binary neutron star signals, if you look at the raw data coming off the detector, you won't see them. They're down below the noise by factors of 5 or 10. They have to be pulled out by intelligent filtering based upon a prior knowledge of what that signal is going to look like. Without doing filtering, you're not going to be able to detect a gravitational wave at all. And so the data analysis is a crucial step. And when the data analysis people, the computer geeks and the theoretical physicists, when they improve their ability to pull signals out of noise by a factor of 2, let's say, that improves the range of the detector by a factor of 2. That improves the volume of detection by a factor of 8. That's like putting in a couple of million euros to upgrade the sensitivity of the detector. So the effort that goes into data analysis probably involves more than half of the people in this collaboration. And it's a crucial part of understanding of the detection. So we've done a lot. We've written lots of papers on our methods. And our methods are generally applicable, that we've developed for digging deep in the noise, are generally applicable to other areas of astronomy. And so other astronomers have been giving us data, and we've, for instance, have discovered in gamma ray data, we've discovered gamma ray pulsars, and another gamma ray pulsar here. That's the person leading this activity is Bruce Allen. He's one of the directors of the Albert Einstein Institute in Hanover. And we're also finding in radio data, we've identified a number of new radio pulsars, just because we have techniques that can get into the noise in anybody's data better than what people have done before. Our searches have been very slow. It's taken us a long time to validate everything. The code is validated line by line with internal reviews. You write a code, you say you detected something. Another committee is formed within the collaboration. They go through your code line by line. You have to justify everything. And then you have to prove that you tested it with fake injections into data on realistic data and so on. There's a huge amount of approval process, validation before anything gets released. And that is a slow process. So one of the things we're doing right now is to make it faster. And we want to be able to give out alerts that are within a minute, let's say, that maybe don't have all those checks in them, but everything's been validated ahead of time, so that when we get an alert, we're reasonably sure it'll be right. And we give those alerts out to astronomers, and then they can see if they can find something else in the sky that might validate the existence of a real event. So we are going to be, initially the data is private, but after the first detection, we're going to have public releases. Our earlier data is now public. You can go and see if we missed any gravitational waves in the data we had back in 2005 to 2010. So there's a lot of stuff here, but we plan eventually to just putting all the data out immediately. And we have collaborations with a number of collaborations you might have heard about, all of which are able to detect transient events, and therefore might be able to see things that are happening in coincidence with our gravitational wave signals. And we now have about 40 collaborations with MOUs for sharing data and looking at these, looking at these things. And so there's a lot of activity in building up multi-messenger astronomy. Now, I talked about locating the sources. I don't want to spend too much. We talked about that with the demonstration and so on last night. It depends. The short burst was what our demonstration was talking about, the clapping and so on. Locating those, you localize that with time delays among detectors, and basically with two detectors you can't do, and what you get is a circle on the sky with just two detectors. With three detectors you can get a good position, but even so, the positions are rather large. The error box is rather large. 10 square degrees might be a good error box. So there's a premium. Now astronomers like building telescopes that focus down to a few arc minutes or something like that, and that they're not happy if you tell them look for something in 10 square degrees. But they're building wide field telescopes and survey telescopes, and they're covering the whole sky every few nights and so on. So there are a lot of astronomers who can actually look in a 10 square degree field of view and hope to find something. Another thing is the pulsars. I didn't talk about localizing GW pulsars, gravitational wave pulsars, but that's a different story. That's something where you use the Doppler effect that I talked about with Lisa last night. As the Earth is going around the sun, you get an imposed phase modulation on a continuous signal from a pulsar. And that really can give you a good location. In fact, it's exactly how radio astronomers get locations of pulsars, and we have the same sort of errors. So down to an arc second, you can localize pulsars with gravitational waves. So it's very different depending on the source of gravitational waves, what the localization is going to be. Now, This year, later on, we're going to come in with these big interferometers, the two Hanford and the Livingston, and the Virgo detectors. GEO is not going to be part of this observing network because it's on too short a baseline. GEO was able to participate earlier because it had more sophisticated technologies. But those technologies were developed with the aim of putting them into these detectors in the upgrades. So now when these detectors have those sophisticated technologies, GEO is left behind because of its shorter baseline. So basically we'll have 3 detectors, which is the minimum that we need for direction finding. The baselines, the baselines are 27 milliseconds, largest baseline. Resolving power of a telescope depends upon the ratio of the wavelength to the size of the telescope. This is the size of the telescope, basically, and the wavelength is actually comparable or even larger, and so the resolving power is weak, and that's why we're not getting very good positions on the sky. What we did with the first interferometer observations was set upper limits. We didn't find any big surprises. We've been able to set upper limits on the rates of things and predict what the rates might be in the next generation of detectors. I just put this diagram. You'll see some more of these later on. This is an antenna diagram of a detector. So a detector that's flat here in the XY plane of this diagram. This is the sensitivity of the detector, the interferometer, to gravitational waves, averaged over polarization in different directions. And you see it's most sensitive up the axes. So if you have a detector that's on the ground here, a gravitational wave source directly above, or below, that's the most sensitive directions. And there are some directions where the sensitivity goes to 0. That's where your wave is coming in at 45 degrees to your two arms, because that's a wave that will influence both arms essentially the same way. That's just the wrong polarization state, and so you'll get 0 sensitivity. So that's where these holes are in this what we call a peanut diagram. But the sensitivity is, apart from those holes, the sensitivity varies by factors of 2 or 3 over the sky. This is the sensitivity of the Hanford and Livingston, the 2 LIGO detectors together. When you put them together, and imagine now there's an orientation here. They're located in the United States. Imagine you're somewhere over the North Atlantic Ocean, okay, and you're looking down. This is the sensitivity diagram. So there's a clear axis where there's the most sensitive detections, and this is with Virgo added in, and it becomes a bit more symmetrical. So we're getting better sky coverage. That's the sensitivity of those of that network. Now I would mainly want to talk about the gravitational wave sources, and so neutron star mergers I've mentioned many times. What are we going to learn when we have neutron star mergers? First of all, we know that there are a number of systems in our own galaxy. We know 7 systems in our own galaxy that are already on the way to merger and have merger times in the range, remaining lifetimes in the range up to about 10 to the 8 years. We can only see a small fraction of our own galaxy. These are discovered by radio observations, and you may or may not realize that radio telescopes, particularly looking for pulsars, they only see the near part of our galaxy. They don't even see as far as the galactic center, and they don't see the other side of the galaxy at all. So we only have a small sample of the number that are in our galaxy. But it's on the basis of that sample and the selection effects in radio observations that the radio astronomers calculate that there are probably enough systems in our galaxy that the one that's closest to merger is about 10 to the 5 years away. That's that number of 10 to the 5 years, once every 10 to the 5 years per galaxy. So there are a lot of these systems around, and if you can have enough sensitivity to measure one or two per year, what are you going to learn? Well, you're going to learn a lot about the equation of state of neutron stars, hot neutron stars particularly. As they merge together, they are very hot, And it's a new form of nuclear matter that you cannot duplicate in the lab. So there are lots of different calculations of what that might be like. We want to actually understand the nuclear physics. So we'll be observing that, and that'll affect the gravitational waves that they emit. You will understand also the mass distribution of neutron stars and binaries. There's a very mysterious thing, which is that most binaries that we know with a pulsar in them, the pulsar is around 1.4 solar masses. And that's a mysterious thing because we believe that you can make pulsars up to 2. In fact, there are some pulsars that are known with masses up to about 2 solar masses. But somehow in these binary systems, they tend to be smaller. And so we would like to understand that. Binary black, we might also have mergers of black holes instead of binary neutron stars. And then that's a very good test of strong field general relativity. And we would, for the first time, begin to understand what the distribution of masses and so on is for real black holes. We don't have any observations of that. There's a good reason to believe that neutron star mergers produce a short gamma ray burst. And that's something that the gamma ray astronomers believe, and so they're very interested in the gravitational wave observations that could be in coincidence with their bursts. But gamma ray bursts are beamed. Gamma rays come out in a beam, and the fraction of the sky covered by that beam is probably only 1%, maybe 3%. But that means that something like 1 out of 30 or 1 out of 100 gravitational wave events will be accompanied by a gamma ray burst that will be visible to the gamma ray detectors. And so it's not going to be an easy thing to make this correlation. So the first network, when we get with our full event rate, we might be getting of order 1 per year in coincidence with gamma ray bursts. But we also are going to have some very strong signals. Our threshold for signal to noise is going to be around 12. Signal noise is amplitude signal noise, and so an amplitude signal noise of 12, if you compare that with an optical observation of a signal noise, that's an energy-based photon counting observation. You square it. So 12, a signal noise of 12 for us is about 100, 150 signal noise for optical astronomers, which isn't a bad signal noise. They're often dealing with much worse signal noise than that. So it's a respectable signal noise. But if you're getting, let's say, 30 events per year when we finally develop our detector network fully, then some of those are going to be stronger. And the strongest ones are going to produce even more science. The strongest event might have a signal noise of 27, let's say 30. Have a smaller error box, we'll be able to pin it down better. And we'll get a better detector, a better distance and so on. We'll be able to identify the counterpart, we'll get a redshift and so on. So that'll help with our calibration, that'll help with the cosmology that we want to do and so on. So there's a lot of stuff coming out of neutron stars. This is a picture from the endpoint of a numerical simulation done by Luciano Rezzola at the Albert Einstein Institute. Rezzola is now at the University of Frankfurt and still doing very interesting simulations of neutron star mergers in full general relativity with full hydrodynamics, magnetohydrodynamics. And this is the magnetic field structure at the end of that simulation. It was a chaotic magnetic field carried in by 2 neutron stars with their own magnetic fields. It was stirred up. But when those two neutron stars merged, they eventually formed a black hole. Once that black hole formed, this magnetic field became very ordered. And you have this polar magnetic field remarkably coming out like this. It wasn't put in by hand. And that's where we think the jets, the gamma ray jets, come from. We think the gamma rays are channeled by these magnetic field lines into this sort of 1% or 3% of the sky. This network is going to be expanded, and we will be bringing in 2 more detectors. So here are the original 4, but we're going to be, so already in Japan, they're building CAGRA. Kagra is short, is a clever name. Kagra has a meaning in Japanese by itself, but it also is short for Kamiokande, Ka, gravitational wave detector, GRI. Kamiokande, if you remember, is where the Japanese have this wonderful neutrino detector. It's in a mountain, inside some tunnels in a mountain. Well, in that same mountain, they've dug 2 3-kilometer tunnels, and they're putting in the gravitational wave detector. And that's very quiet, seismically quiet, to be underground in a mountain. It's a good location. They have a very ambitious detector. They're also going to be cooling it cryogenically, which we don't do with the other ones, to reduce the thermal noise effects. So that's an interesting project, and it's already started. They've got their tunnels, and they've got their vacuum system. LIGO India is still waiting final approval, but we expect it to be approved. India had an election, and then they looked at their science budget again. But it's a cooperation with a close cooperation with LIGO. LIGO originally planned to put 2 detectors in the Hanford, Washington vacuum system, 2 independent detectors. But then it was realized that if you could put one of those detectors somewhere else in the world, you get the benefits of baseline, direction finding, coincidence there. All of those things are improved. And so originally it was offered to Australia. And they said no. They would rather build the SKA, the square kilometer array. And they didn't allocate enough money to build a gravitational wave detector. But then India came in and said, we would like to host that LIGO detector. So the deal is that India builds the vacuum system and all the civil engineering, and LIGO takes all the components that are identical to the components that are in these 2 LIGO detectors and installs it in that vacuum system in India, and we have a LIGO detector in India. So that's what the plan is. We're waiting for final approval for that. But when we have these 5 full detectors, we have a lot more information about gravitational waves. We expect that the rest of this decade will be just the 3 big detectors. We're hoping LIGO India will, this is a little optimistic now, I think the delays in funding will push it back past 2020. Kagra has a target around 2020, and it's going to be difficult to meet that, but it may get there. But by 2025, we will have 5 full sensitivity detectors, and that's going to be much better for things like direction finding. Here's the same map, but it turns out the best baseline is this one between Louisiana and India. You don't see it when you draw a map flat like that. You might think Japan is further away, but actually going through the Earth, as these baselines do because gravitational waves go through the Earth, this is the longest baseline in that network. And so that's already an improvement of 30 or 40% in direction finding. And the fact that you have several detectors and so on gives you even better information about polarization and directions. So when India and Japan come in, we're going to have much better volume. That antenna pattern that I showed you will get more and more spherical. So we'll be covering the whole sky with roughly the same sensitivity and reach. We'll have duty cycle will be much improved because if a detector goes down, there'll still be 4 detectors operating. So we won't be missing events. We'll get better pointing. We'll have better discrimination against these glitches. So we would expect 2 or 3 times as many events, maybe 4 as we improve our data analysis, improving putting more sophisticated data analysis techniques that are possible with when you have more detectors. This is that diagram I showed you before with the present system, but when we have them all, it's much more symmetrical. So we might get 100 to 200 events per year. And with neutron stars, what that means is that the strongest event now is going to have a signal to noise of 60. And so the information you get from really about the neutron star equation of state and so on from these very strong events will be much improved. And we would have a number of gamma ray burst coincidences. And then we'll be able to start testing the cosmology. We'll be able to measure the Hubble constant to accuracies of 1% or so. that's as accurate as the astronomers are able to do it right now. And so it's going to be very interesting to see if we can get a Hubble constant value, which is the same as the optical astronomy ladder. Gamma ray bursts has a lot of interest, and so we'll be filling in a lot of details on that. Black holes are, to me, the most interesting things because we don't see them in any other way, particularly black hole mergers. And we don't even know how to estimate the numbers. We've tried to be rather conservative. Our range for black holes is bigger. We see them much further away because they're much more massive. But the volume rate is probably lower. We're kind of expecting that the rate in our detectors for detecting them is going to be comparable to the neutron star rate, maybe a half of the neutron star rate. But there are astronomers saying no, that there are a lot more black hole binaries out there than the more conservative estimates we've used. So it could be that our data will be dominated by black hole mergers. It just depends upon what's happening in nature, and we really don't understand the black hole binary formation well at all. But on the basis of these rather conservative estimates, we expect to see them out to fairly large redshifts, maybe almost redshifts of order 1, and for the first time get a census of black holes and binary black holes and their spins and so on. We have very accurate numerical simulations now of black hole mergers. We can really compare them with general relativity and test the model of general relativity, test things like cosmic censorship in general relativity. Have you mentioned cosmic censorship? Yeah. It's a conjecture. We believe that general relativity leads to no naked singularities, but we don't know that. That's not a theorem in general relativity. When you're forming mergers of black holes, do you get a black hole with a nice horizon, or do you get something weird? That's something you can test with gravitational wave observations. And again, Hubble constant. So there's a lot more that'll come out. I haven't said much about gravitational wave pulsars. Very difficult to detect because they're very weak. They're not whole stars. They're little lumps on stars that are radiating. So we only expect them from rather nearby systems, probably in our own galaxy. But also, to build up signal, you have to coherently integrate for months, during which time there's a huge phase modulation imprinted on the signal. So it's not simple to just coherently integrate over months. And so the search for gravitational wave pulsars dominates our computing requirements. In fact, we don't do it optimally, even though we know how to do it optimally, because we can't put together enough computer power. So we have upper limits now from earlier observations that are interesting from an astronomical point of view, but we have no detections yet. One way of saying how difficult it is, you have to do your full search over all frequencies for each one of 10 of the 10 different sky locations, and that's an indication of the computing requirement. We do suboptimal searches, and much of this is done on Einstein at Home. Do you know about Einstein at Home? Well, copy this down and put it into Google and go and help us. Einstein at Home is a screensaver. There are times, I know, when you're not looking at your computer screens, right? You're asleep sometimes. And so let your computer run with a screensaver that we give you, and behind the screensaver, we're doing our data analysis on your computer. We download some data onto your computer. We look for pulsars. It's part of the pulsar search thing is the main thing. And then if it finds some candidates, it sends the data back to our big computers, and we assemble this from lots of different people around the world who are doing this. And it gives us a lot of computing power. Right now, we have tens of thousands of participants, tens of thousands of computers, and we're getting more than we're getting close to a petaflop of computing. donated to us by all these people. Hundreds of teraflops. That's an astounding amount of computing, which we could never buy. And so when I ask you to do it, I'm asking you to join a big project. It's not some trivial sort of sideline. This is how we look for pulsars. And the main benefit to us is not just that we couldn't buy that many processors, is that we couldn't pay for the electricity. So when I say leave your computer on overnight, you're paying for the electricity. Okay, so but that's the economics of computing these days, and again, that's run by Bruce Allen at the Albert Einstein Institute in Hanover. So please go to look at Einstein at Home and download it and contribute. And it's a community. We put out, I told you about the gamma ray pulsars and the radio pulsars that we discovered. We put those out on Einstein at Home. That's how we found them. And so there are people in Germany, there are ordinary people who, accountants who have joined this thing and they let the thing run on their computers. And they get an email that says, you participated in the discovery of this gamma ray pulsar. And we want redundancy, so we don't trust any one person's computer. Maybe they've done something to it. So we get redundancy. So maybe we have 3 people participating in this, and they get their names on the website, and sometimes the newspapers pick it up. It's really actually very interesting, citizen science. So that's Einstein at Home. I want to round up lots of other sources. I have a few more slides to get through. Supernovae, as I said earlier, was once the primary motivation for early attempts to detect gravitational waves based upon this number of 10 to the minus 18. We saw how we got the number of 10 to the minus 18, but now we believe it's the goal should be 10 to the minus 21 or 10 to the minus 22. And so it may be that when our detectors are running, if there's a supernova in our galaxy, that we will actually detect the gravitational waves from it, but not from distant galaxies. But if we do, it'll be in coincidence with the neutrino detectors that are running now. And so we'll have a very clear coincidence signal. It'll be very interesting from all the physics. It's hard to predict the waveforms. It's a very chaotic event. So we're going to learn a lot if we can do it, but it's a difficult observation to make. Now, we talked a bit about last night the stochastic background, the primordial background of gravitational waves from the Big Bang, and I mentioned cosmic strings. There's ample opportunity in these places if we can observe these kinds of events to pull out some new physics. 2 LIGO detectors, the way you detect a background, a random background of gravitational waves from the Big Bang, that hiss that I played, if you have only one detector, then it has to be a louder hiss than the hiss of noise from your detector, and you have to have a lot of confidence in this. And if you know the story about the discovery of the cosmic microwave background, that's exactly how the cosmic microwave background was discovered by Penzias and Wilson. They had a radio telescope, and they had a hiss. And no matter where they pointed the telescope, they kept getting the same hiss. And they believed their telescope was better than that. They believed their radio receiver was quieter than that. So eventually, they realized that they were seeing a cosmic microwave background. We would rather be in a position where we can go deeper than the noise of our detectors, and the way you do that is to cross-correlate. So if you have 2 detectors that are getting the same hiss from cosmology, but they have uncorrelated noise, then you multiply those 2 data streams and integrate, and the uncorrelated noise is suppressed relative to the correlated signal. And so we think we can get down to around 10 to the minus 9 of closure density. If the gravitational wave background has an energy density that's 10 to the minus 9 of the average energy density of the universe, then we think we could detect it. What does that number mean? The cosmic microwave background is around 10 to the minus 5. Okay? So we're talking about an energy density that's 10 to the minus 4 of the cosmic microwave background. But that's quite a large density compared to the predictions. The predictions are that it should be around 10 to the minus 15. Okay? So we don't have a lot of optimism that we're going to detect something. If we detect something, then that's great. That's new physics. Yeah, so now we're going to be building third generation detectors, and those are, we hope anyway, after our first detections, we're going to go back to the funding agencies that have been so generous with their money and say, well, we've proved that we can do this, but we can only see a small fraction of the universe, out to 100 megaparsecs or 200 megaparsecs, 300 megaparsecs, but that's only redshifts of less than 0.1. We want to see the whole universe, so we want a 10 times better sensitivity. And that's, we have a detailed study already in Europe that was funded by the European Union for the Einstein telescope, and that will go underground like they're doing in Japan. That will be cryogenic like they're doing in Japan. It'll have much higher laser power than they're using in Japan. It'll cancel out local Newtonian noise. Do you remember in the film yesterday I showed this weather pattern, and I said this remarkable thing that on timescales of about an hour, the disturbances in gravity of weather are larger than the gravitational wave disturbances we expect from astronomy. Well, even at, let's say, at 1 hertz, let's say timescales of a second, if you've got a detector on the ground, you begin to have problems with Newtonian noise. That is, if there's a seismic wave that runs through the rocks, it's a compression wave. It's a density wave in the rocks. It changes gravity locally. And that gravity, those gravity changes on the right timescales of a second or so, are larger than we would expect. And so we'd have to measure them and remove them. We'd have to have seismic monitoring and all sorts of things, and actually remove those Newtonian noise from the data, or cancel it out in some other way. And that's, again, part of this Einstein project. It's a very sophisticated way of extending the frequency range to lower frequencies. And squeezed light, which I'll talk about this afternoon, in the next lecture. It's included in an EU priority list called the Magnificent Seven of astroparticle physics projects, but you can make all the lists you want, but in the end you still have to get the money, and we're not going to seriously try to do that until after our first detections with detectors. But this is a picture that I briefly showed last night of down here, a couple hundred meters deep, 10-kilometer long tunnels with 3 observing stations here, and you can get into them with elevators, and it's very, very elaborate engineering. It's a 1 billion euro project. So that would only be justified if you had good science. And so if you're going to spend that much money, you might as well get everything that's out there, and that system would detect every neutron star binary coalescence that happens anywhere in the universe during the time of observation. And that's a huge population of neutron star mergers, and there's a very rich set of information. We would also monitor all the black holes out to redshifts of 15. Now, redshifts of 15 are very early in the universe. We don't know when the first black hole mergers began to happen, but basically what we're saying is we would see the onset of ordinary black hole mergers and stuff like that. Well, I want to say a few more things, so let's skip over that. Because I do want, I should be stopping about now, is that right?
You've got 15 more minutes?
15? Oh yeah. Oh, then that'll be enough. I only have a couple more slides. I want to talk about the sources for LISA, the space-based things, and a little bit about what's happening for LISA and LISA Pathfinder. If you remember from what I said last night, from space, we're looking at the lower frequency range that's totally masked by gravity disturbances on Earth, so we have to get away. So we're talking about millihertz, timescales of an hour. Again, black hole binaries figures a lot in that, but if you look at what the time scale is, the 1 hour time scale is basically a black hole with a light crossing time of an hour means a radius of 1 light hour, and a mass turns out around 10 to the 5, 10 to the 6 solar masses. So the natural radiators for black hole binaries in the LISA band are massive black holes of 1 million solar masses. It just happens that our galaxy has at the center of it a black hole of around 4 million solar masses. It happens that all galaxies seem to have massive black holes in their centers, and there's a spectrum of masses, but the typical masses of the galaxies we've been able to determine masses for are of the order of 1 million solar masses. So it happens that the LISA band is perfect for exploring the dynamics of the black holes that are a crucial part of the formation of galaxies that reside at the center of every ordinary galaxy. And galaxies merge together, and the black holes are then brought into merger, and you get these binaries. So we think there's a reasonable population that we should be going after, and LISA would be seeing these. LISA would also be sensitive to white dwarf binaries in our own galaxies. Binaries of white dwarfs are smaller masses than neutron stars, and the binaries we're talking about have 1 hour periods rather than the 1 minute periods or less of the coalescing neutron stars that we talked about. So there's lots and lots of systems. We don't have to go to 100 megaparsecs. Our galaxy is full of systems with white dwarfs that have 1 hour periods. And there's so many that there would be a confusion noise in the LISA data. There'd be, at the longer periods, there'd be so many that it actually would limit the sensitivity of the mission. But at higher frequencies, you could see them individually. You could separate them out individually all over the sky from the modulation effects that you get. And so the astronomers are very, very interested in the formation of white dwarf binaries. It's a pathway of stellar evolution to try to understand how stars evolve and die. And so we'll be giving them a huge database of those. And then there's the capture of small black holes by massive ones. I played you the very dissonant kind of music that comes from such a capture. The technology for detecting gravitational waves in space is different from on the ground. We'll talk about the technologies later on, but it involves creating regions in space where you exclude all disturbances. You want something that is pure equivalence principle. You want to have locations in space where it's just the equivalence principle and nothing else, no forces from outside. And we do that by flying inside our spacecraft a cube of metal, gold platinum, and it's free inside. It's in a housing, but it's not in contact with anything else. And it's the reference point for all the interferometry. Then we build a spacecraft around this cube, and the job of the spacecraft is not to bump into the cube. Okay? So there's a force on the spacecraft all the time. There's pressure from the sun. There's all sorts of things happening. But the spacecraft is constantly looking at where the cube is and has little micro thrusters that it fires when it's being pushed toward the cube and comes away again. Okay, so that's the idea of our interferometry. Every one of these spacecrafts has every arm of the interferometer is terminated by two cube at each end, and you have to put these things in space. Well, you have to clamp the cube down to get it into through the rocket ride to get it up there, and then you have to release it, and then all sorts of technologies. There's things you cannot test on the ground. And so ESA decided it would build the LISA Pathfinder spacecraft and put up one arm of an interferometer, but only with an arm length of 0.5 meter. So there's a cube here, all both within the same spacecraft, and we do the interferometry between them. There's not the arm length isn't big enough to detect gravitational waves. It's just a test of the technology. And this has been a very instructive thing. We've been let down by European industry so often because they've never built anything like this, and they would bid for a contract to build it, and oh yeah, we'll build it, and then they don't build it. So it's been an incredibly rough ride to get this thing working, but it has been built. It's now in the final stages of assembly, and late this year it'll be launched by ESA from its spaceport in Kourou in South America. by a Vega launcher. And it'll go out to the L1 Lagrange point to the Earth-Moon system and sit there for about 6 months and just do lots and lots of experiments to validate all the technologies. So we're very excited by that. That'll be the gatekeeper for the rest of the LISA project. And I said right now we're number 3 on the list. We're hoping that if LISA Pathfinder performs the way we expect it to perform, that we have a very strong argument for coming earlier and getting an earlier launch. But we'll see. Basically, I'm going to forget that. LISA Pathfinder has lots of very sophisticated equipment. This is the test mass, that gold platinum cube. You can see the corners here, which are where the clamps hold it and have to release it then, little indentations. And it's inside it sits inside this electrode housing, which capacitively senses the position. You're never supposed to come in contact with the sides of the electrode housing. And then the whole thing is inside a vacuum chamber, inside all of this. And so there's a lot of very sophisticated things that are being built in Italy at Trento University, at the AI in Hanover, at Astrium in Friedrichshafen. So there's lots of contributors to this project. You will see the acronym LISA and the acronym ELISA. We're using them almost interchangeably. LISA was the original project, which was this triangular thing that I showed you in the film last night. The European Space Agency decided it couldn't afford to do that on its own. It wanted a de-scoped project. And so we gave them a project with just 2 of those 3 arms. Still has 3 spacecraft. You have to have 3 spacecraft. And we've called that ELISA. And so that's a kind of minimum baseline, but that ESA is going forward with now. But the idea is we will bring in other partners, China perhaps, the USA almost certainly, and get back enough money to get that 3rd arm. So there's a lot of politics and a lot of strategy here. But I will be talking mostly about LISA because the goal is, of the community is to get a 3-armed detector into space like LISA. If you want to know more, there's a lot of stuff on the web. We even have our own website, elisascience.org, where you can keep up with the latest developments, including LISA Pathfinder. Now, black holes are the main targets of LISA and ELISA. And so this is a sensitivity diagram for only the 2-arm system. And I want to show you something remarkable about the sensitivity to black holes. And this is what sells the project most to the astronomers. What I've got here is a diagram of mass of a black hole system. I'm assuming we're going to have a system with 2 equal mass black holes and merging together. And here's the redshift at which you might see them. Redshifts up to 20. Put things into perspective. Around here, the universe was reionized. So this is at very early times. And then there was a burst of UV radiation from early star formation. And around here, the universe was reionized. It's very hard for astronomers to see through that ion screen and get optical or radio observations back to these very early epochs. But it's at these very early epochs that all the really interesting stuff about structure formation was happening. The little clumps of gas coming together to form little fragments that then merge together, form bigger fragments, and merge together ultimately to form galaxies. All of that was going on through this whole period of time. All right. So, and along with the structure formation were black holes that were being formed, because that's how the black hole in the center of our galaxy got there. It was formed by a merger among smaller black holes that were formed in the centers of smaller fragments and so on. Whoops. Oh. I have pressed the wrong button, and now I don't know how to get back. Let's try this again. Oh, okay. All right. The advanced LIGO and ground-based detectors, they'll explore this corner of the diagram out to redshifts not quite equal to 1, and with masses maybe 10 to the 2, 10 to the 2.5. Those are the first black holes we'll see with gravitational wave detectors. The Einstein telescope that I talked about, the next generation, that'll fill in a bigger range. It'll go out to redshifts around 2 for black holes and up to almost 10 to the 4 solar masses. Astronomers, optical astronomers, and so on, will also very interested in black holes. They go for the other end. It's much easier for them to see the 10 to the 10 solar mass black holes in quasars, and then it becomes harder and harder as the mass goes down. So they can see those out to high redshifts, but then as for lower masses, they can see only to the nearest part of the universe. We're going to be doing pulsar timing and for gravitational waves, which is a way of detecting gravitational waves with pulsars, and that only is the most massive black holes up here, 10 to the 8 to 10 to the 10 solar masses, and that goes out to redshifts of 2, so that's sort of comparable to ET. That's where those are. This is ELISA, and it's a contour diagram with signal to noise. So here's 200, this is 50, this is 20, and this is 10. The outer limit is 10. Signal noise of 10 is a pretty good, is almost around the threshold for detection with our ground-based detectors, but different sort of systems, but that's the sensitivity level. Well, you can go out to, in the 10 to the 5, 10 to the 6 solar mass range, which is where the center of our galaxy black hole is sitting, you can go out to redshifts of 20 with signal noise of 50 or more with ELISA and detect gravitational waves. So ELISA will actually be able to describe, and LISA is even better. LISA, these numbers, these sensitivity numbers get bigger, and the curve is broader. It goes out down to here. But with these space-based detectors, we will actually be able to monitor what actually happened in the early universe as these fragments are forming, and they form their black holes, and the black holes merge together and gradually built up into central black holes that we see in the galaxies today. That whole story, which we only describe today with computer simulations, LISA will make visible. So LISA is the black hole detection machine for astronomy. And of course, there's a region in which we'll have multi-messenger. We'll be able to do joint LISA, ELISA, joint observations with optical and other kinds of telescopes. All right, so the other thing was in the center of that region, for local black hole mergers, the signal noise ratios go over 1,000. And so with that immense signal noise, you can make you can investigate black holes in great detail. We can measure the spins and their directions, the masses to incredible precision. We can measure the distances. We can do the Hubble constant and so on. There's a huge amount of work. Test the O'Hare theorem, test the cosmic censorship, all of those things. I do want to just quickly measure the pulsar timing, as I said before. Groups of radio astronomers, they're making progress. They pool their data. The idea of pulsar timing is that neutron stars, the pulsars, they're good clocks. And so if you're monitoring 6 or 8 pulsars around the sky, and you're correlating the arrival times of the pulses all the time, you can predict, let's say, from 5 of them and study over a period of time, you can predict when the next one is going to be for the others. They're clocks monitoring each other. But a gravitational wave comes in and distorts the travel distance of some of those signals in different ways. And so suddenly it throws all those correlations out. Some of them are delayed, some of them are coming in too soon. And by averaging over a long time, over about a year or more, you can get rid of all sorts of noise and get down to the level where you can see these correlations. And this is a gravitational wave passing the Earth, therefore with periods of an order of a year. And that's why it's very large black holes, 10 to the 10, 10 to the 9 solar mass black holes. And these people are really, really going at it very intensively now, and they're building up sensitivity, and they're not far away from the first predictions. Alberto Cezanna at the Albert Einstein Institute in Golm made a detailed study through the simulations of structure formation in the early universe. Made a detailed study of what the pulsar timing people should be expecting and where they are. And this is an amplitude scale of random gravitational waves. The amplitudes are quite large for these backgrounds. as I was saying to you, 10 to the minus 15 and so on for the cosmological background. This is also for the astrophysical backgrounds. This is a probability distribution, and he's taken many different scenarios for structure formation, and with random number generators, and just run them. So he's got thousands of model universes, and so he can predict in each of the, from this an ensemble of predictions of the gravitational wave intensities, and they're all sort of clustered around here. This is where they are today. This is where the observers are today. They're encroaching on the beginning of this. In about 3-4 years, they should be around here. And so we should be expecting by the end of this decade that pulsar timing will produce its own detection of gravitational waves and a random background of gravitational waves from these most massive black holes that have been formed. And there's now a race. I mean, really, LIGO doesn't want to be the second in this race. LIGO is turning on, but it doesn't know if it's going to be detecting for another 2 years, depends on the source rates. And so it's very possible that the first detections will be done by the pulsar timing people. Okay, this is my last slide. What is it, let me go back, sorry. What is it that motivates us a lot, besides all the things that you can predict, is the things you can't. So every time a new window is opened in astronomy, unexpected things happen. We didn't know about X-ray binary systems until we put X-ray telescopes up and started looking. Radio astronomers were, telescope builders were astounded at how much was out there in the radio universe. So I would think that that would happen with gravitational waves. But when is it going to happen? I don't think it typically we should expect it to happen with the first systems, which are just barely sensitive to detect the things we expect, and where we have to do this matched filtering. We have to know what the signal is ahead of time before we can even detect it. But by the time we get to high signal noise platforms like LISA and like ET, then we should expect, I think, not just the things we know about, but the things we don't know about. And I just wanted to compare that. When did a window open? These are the different windows in astronomy. When was it opened? Galileo opened the optical astronomy window with the first telescopes. The first surprise was right away, Jupiter's moons. Okay, so he violated my criterion that it doesn't happen with the first instruments. Galileo found Jupiter's moons, and so the discovery was exactly the same time as the window was opened. Cosmic rays were opened in 1912. They finally found something really surprising, which was the detection of the muon in the 1930s. Radio telescopes began to be built in the 1930s. They the big surprises were giant radio galaxies, the cosmic microwave background, and pulsars, and they came in the 50s and 60s, not in the 1930s. X-ray observation of the sky began in 1948. The big surprises were the first X-ray binary, that was in 1962, and then understanding X-ray binaries when the first satellite was launched in 1969. Again, a gap. Gamma rays were first detected in 1961 from space. Gamma ray bursts were actually first detected only a few years later in the 1960s. They weren't actually published. You may know the story that it was classified information from the U.S. military. They were looking for gamma ray bursts from the Russians from nuclear tests and so on. They had this network of satellites around the Earth that were looking down, but occasionally they picked up bursts, and when they triangulated with several satellites, they were not coming from the ground. They were coming from somewhere out there. And they thought, oh, throw that away. We're not interested in that. But they did have a few people in the military who said, that could be important stuff for other people. We should release this data. And the general said, release the data, tell the Russians what we can sense, what the sensitivity of our detectors is. No, we're not going to do that. So it took 10 years or 15 years after the U.S. military knew there were gamma ray bursts coming from outer space before the rest of us were informed. So is that that's the surprise event. I hope we don't have that with gravitational waves. I could tell you, I could tell you that some people have obtained funding from the military on the grounds of using gravitational waves to detect, I don't know, submarines and things like that. There are some unscrupulous people who will get money from naive generals. But I don't think we have any of that going on now. Okay, so that's time to, I'm sorry, I've taken almost hour and a half, more than an hour and a half, but okay.
So I think we should invest at least 5 minutes of questions.
Yeah, yeah.
I have a question to the detection principle. You showed that this interferometry light as if there were different path lengths, but the Michelson interferometer in special relativity didn't show it up this way. Can one understand it in terms of redshift, gravitational redshift?
Can I answer that question in my second lecture? Because the second lecture is about detection principles, and I address that point. Yeah.
Yes, actually my question is about one of the earliest slides where you talked about the black hole energy flux. You made an estimate where like it was c to the 5 over g, but that's actually the Planck, or that's the order of the Planck luminosity, right?
Yes.
So I mean, how can we be sure? I mean, these are regimes where we aren't even sure if our models should work. So
Well, remember, just because it's called Planck doesn't mean it's quantum. There's no h bar in that formula. So all that means is that any black hole, and there's no m in that formula. So that formula applies to any massive black hole. It applies to the 10 to the 10 solar mass black holes as they merge together. It applies to a 10 solar mass black hole binary as they merge together. Exactly the same luminosity, peak luminosity. The difference in energy that they radiate is the time scale. So 10 to the 10 solar mass black holes take 10 to the 10 times longer than a 1 solar mass black hole. And so they're radiating at that peak luminosity 10 to the 10 times longer. And they radiate 10 to the 10 times more energy. But it's independent of the scale. The peak luminosity is independent of the scale and doesn't have an h bar in it. So it goes all the way down to the Planck mass black holes, but has nothing to do with quantum gravity.
But this formula comes from the perturbation theory, doesn't it? And if the perturbation is of the same order as the...
That's true, but we now have numerical simulations that verify
So
it.
we should
It comes out, yeah.
You were showing us a simulation of the quasar with the magnetic fields, and I was wondering in the in this picture there we saw the magnetic fields, but they were not closed.
Yeah.
So the magnetic fields were not closed of these spiders.
Yeah. Yeah, it's very interesting. It was not a quasar; it's a gamma ray burst. Although the same phenomenon may be similar to what's happening in quasar, but that simulation was for 2 neutron stars, a gamma ray burst. That's true. You saw these white magnetic lines going out that way, and you didn't see the ones looping around. It's not a perfect dipole field. They are carried away. But what you have to understand also is it's MHD. There is matter in the background that isn't being shown. I just showed you the magnetic field lines, but there's a lot of matter that's streaming out and so on. So it's not a simple vacuum magnetic field. The other thing is that you saw also there was a sort of the stuff in the plane in a different color. That is a toroidal magnetic field. So there's a lot of magnetic field that's circling around that way. That's also associated with the currents, the mass currents in the currents carried by the masses in the MHD, and that's still circling around the outside of the black hole. So it's a very complicated situation.
In one of your slides, you mentioned dry wet mergers. You didn't then afterwards go into it, but can we, would this be detectable, the difference by the resolution of these instruments?
Yeah, so let me explain to people who don't know about dry and wet mergers. That's the reason I didn't talk about it. The question is when two galaxies merge, as often happens, and their black holes are there, their black holes are brought together, and there's kind of friction with the stellar population. As the stellar population becomes less distorted and forms for perhaps an elliptical galaxy or something like that. This energy transfer between the black holes, and the black holes are gradually brought closer and closer together. But then what happens, then the question is, do they get very close together and close enough together to merge together, or do they just stay as a binary pair orbiting forever? And people have investigated this in two different scenarios. There's the dry scenario, which is just a stellar population, just the interaction with the stellar population. And there's the wet scenario, which is where there's a lot of gas as well as the stars, because galaxies do contain a lot of gas. And the gas has turbulence, and the gas has a different kind of dynamical effect on the black holes as they move through the gas and create gravitational disturbances and so on. They lose energy. So there's wet disturbances, there's wet mergers and there's dry mergers, and the wet mergers tend to be more effective. I think that the answer, the attempt to distinguish between wet and dry will be a subtle one, and it'll depend upon a number of things. First, it'll depend upon how many events are there. Are we seeing a larger population of these events, which might indicate wet scenarios are dominant, or smaller than we expect? But also, when we get counterparts, so the idea is to use the LISA error box on the sky and find out what galaxy is actually the galaxy that in which this merger is taking place. And then with X-rays and with optical observations of that galaxy, you should be able to tell how much gas is there. Was this a wet or a dry merger event itself for each individual event? We do think it's not unreasonable to be able to pinpoint the counterpart galaxies, because galaxies in which a merger has just taken place that we've detected with gravitational waves should be highly disturbed, and they shouldn't look like the average galaxy. And so although there's a fairly big error box on the sky that the astronomers have to look at, we think it shouldn't be too difficult to arrive at an identification of a counterpart galaxy.
Further questions? If that's not the case, let's thank